We now enter one very important and wide topic, that is those of constraint optimization. In many contexts, your problem is to maximize some functions subject to some constraints. The function can be linear or non-linear, and you have two ways to solve this function. The first one, this problem, the first one is analytically. For example, with equality constraints, you can look to the Lagrangian method, or you can use first order conditions and then look at KKT conditions for when you have these equality constraints. But often your problem is not solvable analytically. At this point, you can still rely to numerical optimization, where you're going to find the optimal values given your particular data, given the parameter that you provide to the algorithm. And there are some languages specific for constrained optimizations, like GAMS, more used by the economists, or AMPL. And these languages are called algebraic modeling languages because they allow you to express your problem in analytical terms, as equations, and then the job of these languages is to translate the problem in matricial forms and pass it to dedicated algorithm that find the numerically optimal values, and not only passing, so transforming your model from equations to matrix, but also providing the extra information that these called solver engines needs, that is, for example, the first derivative and the second derivative with respect to the variable to the endogenous variable for which we want to find the optimal value. So on one side, we can use these specialized languages, but nowadays, more and more, we can see a swap toward using specialized libraries within a more general purpose language. So there are, for general algebraic modeling languages, I believe the two leading solutions are Pyomo for Python and indeed Jump for Julia. There is many people that come to Julia because of Jump, of this library. And the advantages are clear, because when you have a library within a general purpose programming language, you have a larger community, you have many development tools, like here the Visual Studio Code. You have a much richer language constructs, and also you can interface your specific optimization component of your model with the other part of your model that maybe have nothing to do with optimization. So there is I'm observing more and more swap, people moving from these specialized languages to this solution of libraries for solving optimization problem within Python or Julia. And here we will see how we can specify the endogenous variables, how can we define the constraints of our problem and the objective function of the optimization model, and finally how can we solve it and retrieve the optimal values. We'll have two practical examples now. So here the nice things are we start to see something useful. The first one is the classical transport problem that is in the manual of GAMS, and the objective here is to minimize the transport cost between by moving goods from several plants to several markets, and we have two constraints. Actually, here the original model had two constraints. Here I add another one. So the two original constraints is that we need to satisfy the demand at the market. So we have several markets. Each demand at each market needs to be satisfied, and at the same time we have several plants. The plants have some production capacity. We cannot go more than the production capacity at each given plant. And then another constraint is that there is a limit between, there is a capacity also in the routes between origin and destination, between the plant and the market. So we need to respect that capacity also in terms of individual routes. So we need to use, as I said, this jump package, but jump package itself is only a generic algebraic modeling language. Then we will need a so-called solver engine that do actually perform this solving step of the model. And because this is a linear model, we can use GLPK, that is a very famous linear solver. It can solve also mixed integer problems. So, and here we have some other packages that we need to load the data. I can close for now the plot panel. So the first things I can do here is loading the parameters that will be needed to solve numerically my problem, and define the dimensions that I want, that in some other languages are called sets. So Pyomo and GAMS, for example, have some particular object called sets. Here the sets are just vectors in Julia, ordinary vector. We don't need anything else, but we need to define which are my plants. And here I'm using again example from the forest sector. Here are towns in France with were close to forest resources, and here are big French cities where the data, of course, here is dummy. So we have some sawmills. We assume some sawmills in these 3 towns, and the market in these seven large towns, and we need to transport these 3 different products: fuel wood, sawwood, and panels. Now we need to define which is the supply capacity at each plant of these 3 plants for the 3 different products. So here I did it in a tabular format just to be close to the GAMS tutorial. And here I'm defining here the same data. I'm loading this data in form of a dictionary where I have the supply by using by key as the product and the origin, and I get the relative value. Notice that you can, in general, you can have 2 approaches. You can either use a dictionary as I'm doing here, or you can just use 2-dimensional arrays. Is up to you. Is the same. What is changed is that with a dictionary, it will be a little bit more readable, your model, because you key by the specific sets, the specific value in what we call sets in these arrays of the various dimensions. If you use multidimensional arrays, instead you will have to index by positions. Indexing by positions on one side is a little bit less readable, but on the other side is faster. So if you have big models, I suggest you to use as your parameters multidimensional arrays and look up them by positions. If, like here, you have very small models, just use dictionary. It is much more simple and easy to read. So as I have here now the dictionary where I have the product, the origin, and the capacity of each of them, and I do exactly the same for the demand side. So I specify for each city and the product which is the demand at that market for that product. And as I said, I also put some limit on the default route. So I say that for each possible combination between one plant and one market, there is a capacity limit of 625, whatever is the unit. Now I need to define which is the cost between to supply one product from one given origin to one given destination. So I have this table again, and as before, I put this cost as a dictionary. So the key of the dictionary is product, plant, market, and I have the transport cost. Here again, the data is a dummy data. I just try to look a little bit the geography of the various cities here. Now here, for what it concerns the parameters and the dimensions on which these parameters are defined. Here we didn't use any specific functionality of the jump package. Let's now instead starting the models. So we define our model, we give it a name, TR model, transport model, and we say that this model has to be it must use as solver engine the optimizer JLPK, again a linear solver engine. And also we can give some, we can pass some parameters, so the different solver engine will need different parameters. Here for JLPK is called MSG underscore level, and we set to this is a number actually, and is enumeration, but it is an integer level to fix the message, the verbosity. And we define the endogenous variables. So we with this macro, so variables, the name of the models, and then in this begin and the block we define all our variables. So we define here x variable that is index again here, because is we use indexing by the name of the element in our sets. I use sets as a word. These are vector. These are not sets in the sense of that we saw as data structure sets. These are vectors, but I use sets because in other algebraic programming languages they are defined as sets, but they are just the dimensions. So here for each P in production, for each O in origin, and for each D in destinations, this multidimensional well, I don't know if you define it array or this data structure this variable must be higher or equal to 0. So this is a constraint of this variable, and this variable take as so it's a dense access array, take as a key the various product, the various plants, and the various markets. At this point we have the variables. We needed to define the constraints. Again, we use the macro, these macro constraints, and notice here, so we give a name to the constraint, supply, and again we key our constraints with the the dimension that we need, and we say that the sum of each quantities that are shipped from P to O, for the product P from origin to destination for all the possible destinations must be lower than the supply limit of each product and each origin. Yes. So one important thing is that this is not one single constraint. This is already a family of constraints. So you should see that JUMP explode these constraints that is wrote in very concise way to become a family of constraints for each product and for each origin. And at the same way, these other constraints here of the demand to satisfy the demand at market destination D is a family of constraints, because there is a constraint for each single product and destination combination. And here the constraints, of course, is that the sum for each plant of the product shipped from that plant to the specific destination must be equal to the demand, or higher or equal than the demand for that product at that demand. So it doesn't matter. We sum all the origins from all the plants, and we say that the sum of all what is shipped toward this destination for this product must be satisfy the demand. And the third constraints here that we have for each combination between origin and destination, we need to be below the limit, the capacity limit of the route between origin and destination. So you can see here I'm expressing these constraints in an algebraic form in a very concise way. The last task is finally to define which is the objective, and the objective is of course to minimize the transport cost, and the transport costs are given by the unit cost of a product origin destination by what will be actually shipped, the quantity shipped X between product for the product from the origin to a given destination. And when I sum over these three dimensions, the cost by quantity, I have the total cost. So I can print the model in a relatively human readable form, and I expand here. So you can see here, I don't know why I didn't print. Let me print it again. I think it went over. Okay. I think there is a limit in the number of lines that can be printed, because here I don't have the objective function for some reason, because I didn't do it here. I didn't add it to the model, so this is why. And I can print it, sorry. So here is my objective function. And you can see here that JUMP has replaced my parameters and has expanded my objective. So my objective function is just one function, but it replaced the parameter, the specific parameter. And here, when I put the constraints, so subject to, and here are the various constraints, and you can see what I said earlier, that the supply constraints, for example, has been exploded to all these different constraints, and here are the capacity of the various plants for the various product. So here is the demand, here the supply, and here is the route constraints, and also what I specify in terms of the variables, all the variables that here we need to be optimized, what they will be moved to find the optimal values are the quantities shipped, and this must be non-negative. So here I'm defining the model. The model is ready. It is ready to be passed to the solver engine to be optimized, and this is the place where I optimize the model. As you can see, there is a exclamation point because my model object here changed because it changed and become optimal, found the optimal quantities, and here I can retrieve the states and I should have optimal state. At this point, after the model has been solved, I can retrieve the optimal value. So I can retrieve a set of information, not only the value itself of the roots, but other information as well, as the value of the function, and so the objective value, the total cost here. And you can see here that first I check if the model has been solved correctly, and then with objective value, I retrieve the value of the objective functions, and here I'm with value, with the broadcasted function, I retrieve indeed the value of my endogenous variables. So I decided here you can do what you want. In this case, I loop first by product, and then for each product, I print here in this way the quantities between origin shipped, between origin and destination. With dual, I obtain with the function dual applied to the constraint, I obtain the shadow price. So here I obtain the shadow price of the supply, and here I obtain the shadow price of the demand. What are these shadow price? So let me see a little bit how the output is. So here I print that the problem is correct. Here almost 200,000 is the total cost, and here is the optimal route. For example, for full wood, is not convenient to send from Epinal to Paris anything, but rather sending from Grenoble to Paris and from Bordeaux these quantities here. And here are these shadow price that I was telling you. Well, shadow price are very important information that you get out from your model, because it tells you at the margin how much would change your objective functions if you could relax a bit your constraints. So in this case, we have some constraints on the supply, and this minus 12 applied to Epinal, it's just telling me that because it's a minimization problem, is if I could increase the supply of one unit to Epinal, my transport cost will decrease of 12, let's say, euros. So it's very important economic information, but in general, not only in economics, because it tells you really which are the constraints that bite, where are the constraints that are important. Conversely, here you see Grenoble is 0, but is even if you could increase the capacity of Grenoble, this would not influence of the shadow of the transport cost. While here is the shadow price of the demand is the opposite. So if you could increase the demand of Paris, attention, because your transport cost will increase a lot of 12 euros. If you can choose, put your effort to increase the demand in Lyon or Toulouse, because you will have a much lower transport cost. So here is tell you that if I increase the demand of one unit in one of these cities, which are the results in increase of transport cost, while here, if I could increase the supply of one of these plants, how much the transport cost would be reduced, given that you still transport the same amount of quantities to just satisfy the demand. And here is the same for the other product. So this was an example of a linear optimization problem.